Is it 45 yet? Oh, okay. Let's start, guys. So here we see the same specification we've already seen in natural language. If you remember the traffic lights, requirements, right? North, south, east, west, and the different lights, right? So each direction has a single light with it. Light can be green, yellow, or red. To function properly, they have to obey that if one direction is green or yellow, the other is red. And if you remember, this was our specification translation to predicate logic, or to propositional logic. All the propositions, then we combine them into into compound propositions, and then we gave it as a specification for our system, right? What can we do using predicate logic? What are the benefits we can use? So what are the elements we've seen so far for predicate logic? Like if we take a statement for all and so on and so forth, what are the elements there, like of such a statement? We have what? Okay, we have lights. What will it be? Yellow, red. Yeah. Yeah. So, Jalaluddin, what is it?
Yeah, three lights maybe.
Yellow, three lights.
Green.
It's a set of 3 lights. Our possible lights are 3, and it's a set. What else?
Conditions. We have conditions.
We have conditions. Definitely, we'll have conditions. So we will we have set of lights. What other set do we have?
Roads.
Yeah, directions, right? So how many elements in that set?
2.
2. So set of directions or roads, set of lights. Okay, 2 and 3 elements respectively. Now, since we are using predicate logic, we have to define a predicate. What predicate can we define? What predicate can we define?
Maybe one of some lighting, maybe lighting in different conditions.
Lighting in different conditions. Okay, so even before we talk about conditions, so we have 2 sets, elements that are lights and or colors, and elements that are directions. Can we connect them through a predicate? Because predicate is a relation, right? What can be a predicate? Is color. And what does that mean? The meaning of it, the semantic meaning of it. Yes. So is color, direction, color, whatever we can call it, but it's better to give descriptive name. But the main important thing is that it takes two parameters on 2 terms. The first one, let's say, is direction. The other one is color, and says that this direction is this color. Okay. Now, what do we need to specify? Each one has one light associated with it, and it can be green, yellow, or red. How do we specify that in predicate logic?
Maybe we should use that only one green light.
Unique identifier, okay. Yeah. Unique identifier would allow us to say that direction has 1 light on, right?
So there exists only one. I want to say that there exists only one direction, but have green light.
Okay, this could be think, yeah. There exists only one direction that has green light, and so okay, and it works for 2 roads, right? If we have 2 roads, then only one of them can be green. Okay. We can also specify that only one color can be, for one direction can have 1 color. I mean, it cannot be green and yellow at the same time, right? And then we can say that if like, so long story short, because I want to move on, this is the specification that is suggested to us. So as we said, directions and colors. And this predicate LXY, where X is direction, Y is color. Okay? What does the first one say?
All directions instead of directions. There is a color, maybe.
Yeah. So, and in English it means
That for each direction, there is some color.
yeah. So each direction has some color. What does the second one say?
There are no equal colors or two directions.
On two directions. No, there are no two directions. Here we're talking about one direction, right? Because we're saying D.
And every direction has only one color.
Yeah. So if basically it's saying if colors are different, they cannot belong to the same direction.
Yeah.
Okay? So here we said that there is one, and for sure, here we're saying cannot be two different colors for the direction. So that's it. And together they cover the part that every direction has a color associated with it. What does the second one say? Or the third statement? Yes, yes. So first of all, we are saying that for any two directions which is not the same direction, for any two different direction, if one of them is green or yellow, the other one is red. Okay, that's it. That's it. So, and we've specified using 3 lines the same condition we specified here. It just demonstrates that predicate logic is more concise. And beauty of it, one beauty of it is that it's more extendable as well. So now imagine we have a new direction opened. Or like we want to have an extra color or whatever, right? So using then, like for many scenarios, we will not have to change the properties. We just need to expand the sets. Okay. So it's
What
more
does R meaning here? Can you say?
R, this one.
Yeah.
It's just the name of the rule we gave.
Ah, okay.
It's our naming. So we're saying that this, we define it as this, we define it as this. And then we're saying that these are these three colors, or these 3 rules give us traffic lights. Okay.
Okay.
One thing that I want you to kind of pay attention to is the fact that normally we declare different properties or we specify different properties of the program, combine them together, such that it is a holistic program, such that they what it's called, дополняют. They sorry?
Extends.
Yeah, they extend each other, you know. This is basically, they work together, right, in harmony. Same thing here when we talked about phasors and so on and so forth. They can be taken together to give you, to define somehow what does it mean to, what does being a phasor mean and being a cyclic mean, like some system of relations, right, of blood relations. Now, traffic lights. This is also like practice if you want, but I think we have also in-class practice, which I think each one of you can get. Jaludin, I will share with you. I will share with you on Telegram. I will get a copy as well. Okay. And also maybe let's open it, right? Okay. So a red-black tree is a special kind of binary tree. So we are talking about binary trees here, right? Binary tree is a data structure which is balanced and has all its nodes colored either in red or black. There is only one root node, and each node can have 0, 1, or 2 child nodes. Okay, so it's a binary tree. What does binary mean? 2. Yeah, so 2 to 2, like that's how branching goes, right? So, and every node is either red or black. Then we have a bunch of things made ready for us. Okay, so it says that N is a set of nodes, of all nodes. Leaf, it means like a leaf of a tree. Root is the topmost, right? Leaf are the things that are at the bottom. And then something can be black, something can be red, a node can be red or black. Then a node can be parent of another node. And node can be in the left subtree. So somewhere basically it's a descendant on the left side or descendant on the right side. So they defined a bunch of predicates for us. And this is a system that is called RB, red, black, tree. Now, here, and this actually was, I think, midterm retake last year or whatever. The midterms that the last year's group had was in-class things that they wrote like an exam. For you, I'm preparing something more interesting, a project, okay, which we will talk about later. This point, and this thing, let's try to translate it very quickly. So 10 rules we have to define. Each red node in RB has exactly 2 black children. Each red node has exactly 2 black children. How do we define that? Any ideas? Sorry? For all n in n, okay.
Then predicate red and implies that okay.
I think you were going in the correct direction. Okay. Okay. So again, yeah, Alexei, please. For all n, and 1 and 2 and 3 from n, okay. So they are all nodes, Each red node RB has exactly 2 black children. Okay.
So we should say that node, so its parents, let it be n1 parent of n2 and n1 parent.
Okay, so parent n1 and 2 and parent n1 and 3, right? So okay.
And n1 is right.
Can we do in the different way here?
Yeah, we can, but let's try to hear out what Alexei has. Okay.
Oh, okay.
N1 is red. So red and 1.
And red and 1.
And black and 2.
Black and 2. And black and 3. What did we say here? Like what did we say?
We have the N1 is red and have two child. That's our way.
Okay, but we're saying for all N1 and 2, so for all nodes in N, this is true basically, this we're saying. But it says for, what does the condition say? It says each node in RB has each red node in RB has exactly 2 black children. So each red node has 2 children. Any ideas, guys?
Maybe all black N
Okay.
exist as there is 2 children. Maybe we can combine existing quantifier and universal quantifier here.
Okay, we can use existing quantifier. I think that's a good idea. Okay, so but what is the first thing we have to establish? Because this is not true for everything. This is true only for a certain set of nodes, right?
Each black, maybe for all black.
For why black? No, for all red, right?
Red.
Implication. So for each node that is red,
Yes.
implication to child.
Okay. For all here, we don't even need implication. We can say for every black, for every red node, there exists, we say 2 children, right? And 2 from N, such that parent and 3. Okay. Okay. So here, what did we say? What else is important to say here to establish that it's 2 but not less than 2? And 2 is not equal to N3. Okay. So now we said that, what did we say here? Every red has,
yeah.
Say that's not all the others, so it's only 2, so we should say that all other that is like N2 or
okay. And for any other node which happens to be child of N4, it means what?
They N4 equal N3.
Or N4 equal N2. Yeah, I think this is it, guys.
What does it mean last?
The last sentence. So here we establish that it has at least 2 children, right? Here we said that there exists N2 and N3 that are children for it, and they're not the same. So at least 2. But we're not saying that exactly 2.
Yeah.
There can be more, right? We're silent about maybe there's 3rd one.
Why more? I think this assumption can have more.
No, that's the thing that, like, I mean, if we had a rule which defines that a node can have only 2 children, you could do it. For example, you can say that for all nodes there can be maximum 2 children, you know, and any 3rd one is one of them, if it has. But for now we don't have a rule like this, so we are defining everything within one rule.
By the way, our children can be black or red.
That's it, right? So, like, what do we have to say? Where we have to say it? Where we have to say it?
First line and
Uh-huh.
black and black and 2 and black and 3.
Uh-huh. And black and 2 and black and 3. That's it. So they're both black. Exactly 2 black children, and anything else is one of them, you know. Okay, good. Each red node in RB has exactly 2 black children. Okay. A red node cannot be a child of another red node.
not exist.
There does not exist. Okay, this is a possible thing to say. Okay, so how would we say it?
Exists somewhere, exists.
Okay, just a second, guys. Let me clean it up, and I need to copy the things again. Okay, so let's go back. Okay, so what do you want to say? For all, some n, right? Uh-huh. Uh-huh.
Which is red, so red and
For all n, no child may be red, yeah.
Red n. Okay. Then
Implies maybe
implies. Uh-huh.
not child.
Not parent. We don't have child, right? We have parent.
Okay. Parent.
And N1, but where did N1 come from?
not exists, which is
Yeah, I think like, let's call it N1 and N2, right? So N1 and what is missing here? Okay. Red and 2. So here we're saying, yeah, a red node cannot be a child of another red node. That's it, you know. We can also specify that they are not the same, so the thing cannot be son of or child of itself. But I think it's fine. It's like we cover that here. We cover that a red node cannot be a child of itself as well. Okay, a node is either red or black, but not both. I think this one is easy, no? So, okay. Okay, so for all n from n, okay.
and red and
The dot, okay, so let me put a dot like this. I don't know how to put the dot. Red
Or black.
black n, okay, or black n. So it's either red or black, but not both.
red and not black or black and not black.
And not what?
We need black is so red n and not black n. Black is closing, then or black is opening, black n and not red n.
Like this? Brackets, the first brackets, or
Yes, I understand. And between them and not black n.
not black n.
No, in brackets we have red n and not black n.
Okay. And red n and not black n.
Yes.
Black
I mean in the previous brackets.
Where?
Previous brackets.
Here.
Yes. Red n and not black n.
Red n and not
No.
black. Okay.
Here we put red n and not black n, or red, not red n and black n.
Okay. This is another way to say it, right? Red n and not black n. So basically this one, or black n and not red, and not red n. Yeah, I think this is another way to say it. Or we can say red or black and not both, and not red and black. This is also another, but I think the semantically they're the same. Okay. Okay. All leaves are of the same color as the root. Okay. So all leaves are the same color as the root. So all leaves, let's do it quickly, guys. How do we do all leaves as the same color as the root?
For all root has the same leaves, maybe.
Okay, for all roots have the same leaves. Okay,
Yeah.
so for all, yeah, for all n, let's say. What? Okay, so here we're talking about leaves and roots, right? So it means we need at least two variables.
Yeah.
Okay,
Let's do one.
and one and two.
And
Root and one. What is the root? Okay, root and one.
we should have leaf.
And leaf and two. Implies.
That they both red or they
Okay.
so red and one red and red and two. Red and one. No, the color.
Abstract color.
Color
We could introduce new predicate, yeah. If we introduce new predicate, but otherwise no. Otherwise we have to say.
I think we use color for all and
Priority is the same as another. So if we have four, it's like disjunction of conjunctions.
Yeah.
We can not use brackets.
Yeah, we don't have to. This is just for readability, maybe.
And second was, we can maybe define some another predicates to simplicity, maybe some maybe red root, black root, or something. So we can have a lot of predicates to simplify some definition of another roots. Yeah.
Again, I didn't get.
We have like red root, black root,
Yeah.
red root, black root.
Yes.
It can be a lot of some predicates, but rule will be short.
Yes, yes. We can introduce new predicates. And I think that's what Timur was saying as well. We can introduce predicate color. So instead of writing red and black, just put the same variable. Okay. Good, guys. Okay. So I think like probably you, I hope you got somehow hang of predicate logic. So fathers and children. One thing that you can do, you can also declare predicate logic in Z3 and it will work. Okay, you can check for satisfiability. So if you bring all the rules together, if you're defining rules or properties of a program, you bring them all together, they have to be satisfiable as a whole, right? So here are other things. What can we notice? So predicates are declared as functions that return Boolean. This is exactly what we were talking about in the beginning. And then you have this for all asserts. So like you can combine them together into one in once like one after another. Okay. and then check satisfiability. So you declared all of them, check satisfiability. Similar syntax you can use for your assignment action in terms of declare all the asserts and then check satisfiability. Okay, because I think you have assignment like this for propositional logic. Okay. One more fact is that there is universal quantification inference rules. So there is introduction, how universal quantifier can be introduced. And here's the thing is that if you assume some random A, some arbitrary A, and you show that for arbitrary A from that set a property holds, since it is arbitrary, which means any, it means we can introduce universal quantifier. Okay, that this rule holds for everything in that set. Okay, elimination is quite simple. That if you have a rule that for all elements in some set this property holds, and you know that some element, not arbitrary, but a particular element belongs to that set, it means that this property holds for that element. Okay, so kind of combination of two gives you the implication, which this is introducing universal quantifier, eliminating universal quantifier. And similarly with existential quantifier, you can introduce and eliminate it. Introduce and eliminate it. So how do we introduce it? If we know that some element belongs to a set and a certain property or certain predicate holds for it, we know that there is at least one element in that set for which this property holds. Makes sense, right? And elimination, elimination is a bit different here. What does it do? So if there exists X, some element in S for which the property holds. And if you assume okay, that's it. That's it. I think I figured out. So if we like, imagine we assume that if these assumptions leads to some logical conclusion, if assuming this, that some element belongs to S and the property holds for that element, if it leads to some logical conclusion, let's say that like if we assume that the room next to us has a bear inside, and bear is hungry, okay? If we assume that the room next to us has a bear inside and bear is hungry, we can make an inference that if one of us enters that room, our life will be in danger, that the bear can eat us, right? This is assuming that there is a bear and it is hungry. Entering that room is dangerous. This is our assumption. Then somebody comes to us and says, there is in fact a bear. Then together they give that, okay, entering that room is dangerous. This is a like silly example, but like basically, if you have assuming something leads to a certain conclusion, certain result, and you know that this assumption is in fact false, that there is at least one instance of that assumption that is true, it means that the result is in fact also follows.
For example, this example with it's not false forever. I mean, if you go and check, one person goes and check, another go and check, the bear will be not hungry. For first 5% or something, it's true, but for next one is not true.
Okay. Yeah.
Are here conclusion, yeah, you mean?
R here is result, yeah. So basically we're saying that, like, okay, imagine the room next to us, obviously there's no bear. Imagine we live in a village. And we're saying that A is a bear. So some creature that belongs to the family of bears, right? And it is hungry. If a hungry bear is around, it is dangerous to go outside. So if our village has a hungry bear walking around, it is dangerous to go outside. But it's assuming this. But then, in fact, we know that there is at least one hungry bear outside. And then Alexei is saying, but if it's one person, then that's it. You know, the first part does not hold anymore. There's no more hungry bear, so it's no longer dangerous. I mean, we cannot conclusively say that it's not more dangerous because maybe there are wolves as well, right? So and other things can lead to R as well. This is correct. This is actually very important. This is how science works. For example, like if we talk about science, scientific method uses this. So we observe fact B. We say, let's assume fact A, then it would explain fact B, right? That's how any scientific theory is. It tries to explain why the things the way they are, okay? Does it make, and for example, yeah, so if fact B, we're observing it, if A was true, it would explain B. Does it mean that A is true? If something has explanatory power, does not mean that it's true, because there can be other things that explain it even better. So yeah. Okay, guys. This is predicate logic. In terms of like for specification, you need some theoretical basis. I think logic was the heaviest part of it. There's also discrete mathematics, like functions. Yeah, I think total functions, partial functions, this stuff. If you haven't studied it, you will need to wrap your head around it. But the heaviest kind of formal stuff we've covered. Now, the question is, how does it affect us as software engineers? How can we use it as software engineers? Now we have the basis and we're kind of somehow comfortable with formal specification. One instance that is directly applicable to us is something called design by contract. Okay, design by contract. Let's talk a little bit, have like a historical note. You know this paper, right? Axiomatic basis for computer programming. You were reading it, you were covering it last lecture. This paper introduced something called Hort triple, about which I was asking about you in the quiz. What is Hort triple? Precondition, program or implementation post-condition. This is the idea that Hort introduced in year 69. And it's not the central idea of this paper. It's a complementary idea that he uses to go further, to show that using precondition, post-conditions, we can establish some properties of programs, prove them in fact, right? But this idea is very elegant, in fact. The fact that there is observations that when we're declaring software, most of the time we want it to do some things. So we're reasoning about methods. What can it do for us, right? And we want to observe that our program has certain properties before the method is being executed, so as an entrance and after. So then comes Bertrand Meyer, this guy, touch of class, who is also was in your reading. He actually was professor at some point here. He's still visiting professor. He came up with the idea of design by contract. And he said that, and he really built upon this horse idea, that precondition, postcondition, why don't we use it to write more robust programs, better programs? And he actually kind of even he called it contract, actually, something that you kind of agree to follow when you're using this program. And that's the definition he gave to it. A contract is a specification of properties of software element that affects its use by potential clients. Specification of properties, which we were doing a lot, right? I mean, even today, of a software element. So element can be program, method, whatever, that affects its use by potential clients. So this is for clients, for the users of this thing. It's not about the implementation, it's about how it is in use, right? So contracts are requirements embedded in code. This is like the beauty of it. That's what I want you to feel like until the end of this lab. But when we're talking about affects its use by potential clients, it means they put constraints on the interface of a class. They put constraints on how the class is used. Please come. They put constraints on how the class is used. What are kinds of contracts? One is invariant. What does invariant mean?
It's all for all cases.
Yeah, invariant is something that doesn't change, right? That's the meaning of it. Bertrand actually, what he did, he declared very. We actually even looking before looking at the invariants, pre and post conditions we're familiar with them, right? We're familiar. Precondition feature must make sure that the precondition holds before the call of method. Post condition that it calls holds at the end of the executed method, right? Something we're familiar with. If you think about it, what if we have a post condition that is true for all methods we run? What if we have post condition that is true for everything and a precondition that is true for everything? Or what if we have something that is precondition and post condition for every method in the class? One thing we can do, we can put it in the beginning at the end of each class, right? But then a smarter thing would be if it's true for, if it's a, you can say that universal pre and post condition that has to be true for all classes. That's he introduced an invariant. Basically, that's what invariant is. Class invariant must hold as soon as an object is created. So as a creation, so as a constructor method at the end of instance is constructed, invariant has to hold already. Then before and after execution of any of the class features available to clients. So basically, and then it serves as precondition and post conditions for any call, for every method. That's what invariant is. So in fact, if we're talking about Tony Hoare, he's not talking about invariants. He's talking about precondition, post conditions. But important to understand that invariant by itself is a specific case of a pre-post condition. That is, you can say, even look at it as syntactic sugar, you know, some more concise notation. So let's look at invariant. And what Bertrand did, he took it further. He actually invented a language of his own, IFO, where he tried to make it part of language. So when you write code, you embed it into code, these pre-post conditions. So when you declare a class, let's say you are declaring a class for train line. So you are operating the trains on at some train station or whatever, and you have lines. Okay, so lines is like a магистраль железнодорожная, right? That leads from one station to another. And you can declare invariants for your class, which is train line, right? That there has to be at least one station. At least one station of the train line, because what is the line without any stations? What's the point of it? And then you are saying that south is first, north is last. That the south end should be the first station, the north end is the last station. This is another invariant you are declaring. Some rules, right? So basically, you are defining, you're embedding some of the requirements inside your program. And now it becomes part of your code. Identical ends if empty. So basically, if there is only one station, then south end and north end are the same station. So both ends are the same. Okay. Now, if you imagine you are declaring invariant for train odometer, which measures the distance that it's kind of the distance and speed and so on and so forth. So it says that the final reading in terms of the distance covered should be initial odometer reading plus whatever they covered. trip time on average speed. Okay, this is also, and this makes sense. So invariants are things that have to be always true. Now, what's the benefit of it? What is the benefit of it? How could this be useful to you if you're writing a program? Sorry? For testing, yeah, for testing. And especially for what it's called, reverse, how it's called? I think reverse testing, right? Or what is the name for it? When you check that you didn't break anything that was already working. How?
Regression test.
Regression, yeah, not reverse, regression tests. So when we update programs, we tend to break things that weren't broken before. So it's useful at the beginning, but it's useful for you to have a safety check. So if you've broken something, one of it will flag.
At the same time, it can be test-driven development because you write the contract first, you write the invariant, you write the precondition, post-condition, and then write the implementation.
This is the main idea, guys, that we're trying to tell you here. So if you've got requirements, you remember all the programs or properties, we were traffic lights, whatever. Everything we were doing, they weren't post or preconditions, they were invariants.
Similar like unit tests.
Similar like unit tests, like test-driven development. So what do you do in test-driven development? You are thinking about requirements and you say, okay, what will be the inputs, outputs, what should be the expected behavior? You write the test first. Here, it's a little bit different because unit testing, what it does, it tests specific input, specific output, right? For this specific input, this specific output should be true. It's a very elegant idea. Design by contract is a little bit different. You're not thinking for what input, what output should be true for specific case. You're saying what properties of my program should be generally speaking. The fact that traffic light should not be two colors at the same time. You see?
And this is actually a kind of testing, they call it property testing.
Yes.
In languages such as Haskell, there are libraries where you define a property and it will generate 100 or 1000 or how many test cases to test this property. So
Nice.
you declare a property and it will try to test it with all.
So like it will generate random test cases, right?
It will generate them smartly to test the property. So if your property is something that has to do with integers, you test with 0, with int max, int min, something in between,
Yes.
and so on.
Yes, yes. This is amazing. This is amazing. So one thing that I want you to like when you've got requirements and you are translating it into program, one thing is to sit and write implementation straight away. Another thing is to think about the properties of your program. What should be the properties that should always hold? If you're talking about unit testing or test-driven development, you should come up with some good inputs, right? What are the strategies for coming up with good inputs? You're taking functional testing right now, right? Black box testing at ASA. What are some of the smart ways to find these inputs? Where errors normally come? At what points? At boundary cases, right? So this is the logic that, like, for example, in ASA, they're teaching you how to find good test inputs that will likely reveal errors. Here, you are looking at a little bit different approach where you're doing property testing, as Abdurrahman says. And you can have programs where you can have frameworks that will generate the test cases for you. And if I was designing a framework like this, I would try to generate test cases for boundaries as well, you know, if I really want to generate something smart. Pre and post condition, a client calling a feature must make sure that the precondition falls before the call, after the call. Fair enough. Let's see how it is implemented in the thingy, in Eiffel. So here we have a class which is defining some matrix operations for us, right? And one of the operations that we are declaring is addition of two matrices. It's a very good use case to declare some pre and post conditions. So preconditions, we use word require, and it's quite common. It's used in other languages as well. The post conditions, we write it with keyword ensure. Most of the time, other languages use assert. Okay, require, assert. Sometimes languages use assert for everything because at the end of the day, it's like it just says make sure, right? require and ensure it's just to make it more readable. You give tags some kind of names for your preconditions, but this is not, you don't even have to declare this part. The only thing that you have to declare is this. So what does the first one say? M minimum size. What does the first precondition check?
We should have arrived at this one.
Yes, so the matrix cannot be less than one row and one column, right? Okay, the second one is checking the same for the second matrix. What about the precondition 3 and 4?
We should have equal.
Checks equality of width and height of two matrix.
Yes, because to add them, they have to be of the same dimensions, right? The same size. Okay, and in post condition, what do we write? The same, right? But for what are we checking?
We check the results.
Yeah, for the result of addition, we are we're checking that they have to be the result has to be the same width as the input and the same height. This one is just saying that it's a class level static method, but don't worry about that. Implementation is in between. Okay. In fact, when you see the interface as client of this method, right? As a user of this class, you will not see the implementation, but you will see the pre and post condition. So it's on one hand, you are taking some requirements that make sense in your case. You are making your program more robust, right? And also kind of designing it in a way that, okay, trying to first think of how it should work before implementing it. And the third benefit is that you're documenting your code for the users. Knowing the pre and post conditions and giving the size, the names and stuff like this gives you basically a well-documented API for other developers to use. Okay. These are the benefits of using design by contract. And in fact, we will see cases where we will, and this will be a midterm, you will get a specification in natural language. We will not work in Eiffel, but we will work in another language, and we will also see how this is. Eiffel is a language that kind of has this concept embedded inside it, like as part of the language. Other languages have hacks, workarounds, how to use the same thing, but like it's just not as beautiful, but the idea is the same. Like one of the problems when you're dealing with requirements is traceability. In terms of you get requirements from client and then you get implementation. And important question is, why did we do things as we did them? Where did this come from? If we're making some functionality in a certain way, where did it come from? Who wanted it, this way? The traceability is important. And normally what companies who are very good with documentation, what they make, they have traceability across stages. Initial requirements, implementation. So even for like when tasks in Jira, they also have a connection to the requirements, right? And then for the test cases, they know which test case tests which requirement. And it's like a matrix checking all of it. Design by contract is a tool that allows you to do it all in code. Because maintaining a separate documentation of your requirements as a separate document and keeping it up to date, test cases, fair enough, you have to keep them up to date. And code base, 3 different artifacts, traceability, keeping it all updated is difficult. Design by contract, the idea is make your requirements, your test case, and part of your implementation, and bring it all inside the code. This is the most sure way to keep them up to date. Like if you think about it, very elegant idea. There are also loop invariants, but I mean, I don't think that, I think you had enough for today. So this is not related to design by contract as such, is that it only checks that the loops that you don't have infinite loops. So Eiffel also has this instrument to make sure you don't have infinite loops, which is another touch of
The value of the
yeah. But the variant also checks that you exited correctly and so on and so forth, right?
the invariant, yes. But the
Yes.
invariant is to check that it's not an infinite loop.
Yes. So you have some elements, extra elements for the thing, but they're not essential to the design by contract. Now, what we're seeing here, we want to see how contracts work out in other languages, because Eiffel is not used much in industry as production language, right? What language is this? Python, right? Python is probably the most popular language out there. You can define class circle, and you need invariants, preconditions, postconditions. So pre and post conditions are quite simple, right? You put asserts in the beginning and at the end of method. You can, and interestingly, look, when you make an assert, for example, here, radius is more than 0. Put a message that should be put to the console if this invariant is violated. But also, this is a way to take your natural language requirements that were in the beginning and put it as a messaging for your. So in other words, you even natural language, you're bringing it in the code, and it has several useful purposes. It's more readable as code, but it also flags you the problem. It gives you very nice debugging experience, right? Invariants, we are using a workaround. We are declaring a class invariance where we declare all the asserts that have to be true at all points, and we call it in the beginning and at the end. It's a workaround, still, but it allows us to have invariants as well. If you don't like this, you can just use the pre and post conditions. This is without using any libraries. Apart from that, there are libraries like PyContracts that uses like gives you things like this a decorator which you can use to declare to specify your pre and post conditions. Okay. Similarly, Java has even I think a more but a more full implementation of the concept, where you have not only preconditions, postconditions, but even invariants. And you basically, these are the things, and that's how you declare them. Invariant, this is for the class, right? And requires is the precondition. And then you can also specify the postconditions. Let me bring an example. Ensures postcondition before each method. This is as a library, but you don't have to use any libraries. That's not the point. Requirements are tests. Requirements can be your tests. And we are pretty much done for today. The last thing that I want to describe to you is the midterm assignment that you have released on Monday. Okay. The requirement will be a specification. So up to this point, we were mostly covering theoretical stuff which does not have direct application. Now we are you will deal with an actual program, a real life program. What it will be about smart contracts. There is a language called Solidity, which is object-oriented language similar to JavaScript. It allows you to create contracts, smart contracts for Ethereum framework. Okay. You will have a natural language specification for a contract that I want you to create. And your job will be to use this design by contract methodology idea to embed it into your implementation of this contract. And as an intermediary step, I think we will use, you know, UML class diagram, all of you know it, right? UML class diagram. It has an addition to it called OCL, Object Constraint Language, which allows you to add pre-post conditions to class diagram. Okay, so we will, that's the schema we'll have. Natural language requirements, you model it using this semi-formal notation of UML class diagram, made more formal through OCL. and then implement it in using smart contracts as a real smart contract program. Okay, that will be your midterm. Now, what do you need as skills? What do you need to implement such a midterm assignment? What are the elements? What knowledge do you need for that? How to work with Solidity, so building smart contracts. Okay, what else? Everybody knows class diagram. Like, not familiar, but knows, can produce a class diagram. Yeah? Okay, Daston, Jaladin? Huh? Yeah, UML class diagram. Okay.
Yes.
It's very good. So we will not spend too much time exploring how UML class diagrams are built, but we will see OCL, because I'm sure most of you are not familiar with OCL. So next lab, we will have a workshop delivered by Hamza, who is very good with smart contracts. He will teach you the basics of building smart contracts, so you have all the skills required to implement. We will also cover UCL, or OCL, as it relates to class diagrams, so you have all the skills required to specify the given natural language requirements. That's it. Yes, Hamza Salim. You know him? Yeah, yeah. So he's my classmate from MSIT, and he teaches blockchain, and generally he's like very, very smart guy.
So the deadline by the 2nd and 7th of Monday, they will be 10 or 7.
Yes.
What
So
will be the deadline for the midterm?
I think like currently I put it on Friday. So on Monday you are getting it. Obviously not Friday the same week, but Friday after. Okay.
So we'll be
10 days, 12 days,
Yeah.
12 days. But importantly, guys, all the skills necessary for implementation, except class diagram, you will get at the lab. So OCL and contracts, you will get at the lab on Thursday. You get the assignment on Monday, you get the skills on Thursday. What should you do in the gap? I mean, I'm sure you have a lot of things to do. One smart thing to do will be to produce class diagram, to think about class diagram, because you already know. So maybe think about that part. Familiarize yourself with the requirements, because it will be like a proper, an actual case for using smart contracts. So familiarize so that you can ask intelligent questions and think. When Hamza is teaching you how to build contracts, you can be thinking about how will I be building it for the midterm assignment. Okay. That's it, guys. I think let's finish a bit earlier today.
So with the midterm, we should submit the diagrams and the implementation. Right?
Yeah. Yeah. Yeah.
By the way, how's it going with assignment 2? I think no one submitted anything yet. With test.
I have a question for the test. Do we need some restrictions on how to submit the implementation? Or we just submit a code it will launch?
Yeah, I mean, everything is written and the context is set. You just read from a file, its name is provided, you write to a file, its name is also given, and it will run.
Yeah. And please make your code readable somehow, because we'll look at it.
The line for sector 7 is Monday evening. Right?
Monday evening, yeah.
And we will have those.
On Monday, no.
We have a year on Monday. We should ask about it today.
I thought. Okay.
Tuesday.
Tuesday.
So guys, Tuesday is holidays. That's why I was thinking to move it to Monday, but then Manuel was saying, okay, give them a break, and Abdurrahman was saying, give them a break, and okay, so you got a break. But like Thursday, we'll have it as usual. I mean, it will be kind of part workshop, part OCL. Monday, speak to Sasha, to Alexander, yeah, because I was speaking to him. He was saying that he's thinking about whether to have it.
Thank you.
Okay, thank you, guys. Bye.
Thank you. Bye.
Thank you.